Hey there, long time no see. I was talking to some people the other day about some of the work that I was doing on Aux Labs, and they found it pretty cool. So I thought that now might be a good time to record a little introductory video going through what I've been working on and kind of show you how it's intended to be used, how it works, how it functions, and hopefully get some people interested in helping out because I think there's some really cool things that we can do with this setup. So, first off, what is Aux Labs? The idea is we wanted to experiment on a handful of things and we wanted to build some new, like brand new projects that weren't built off of an existing niche packages or things like that. And we wanted to put them somewhere without just creating a whole bunch of repositories with random names that would be hard for people to find and hard to remember where things are. And so to solve that, we have just one repository where a whole bunch of experiments can live and kind of coexist together while we're working them out. So that's what Aux Labs is a place for experiments. And the experiments that we have right now are right here. We have Aux Lib, we have Aux Foundation, and we have Aux Tidepool. And we're going to go through them in that order. And I'll show you what each of these is about. So starting with Aux Lib, you might already be familiar with Nix packages lib, right? You have a library of Nix functions that are commonly used, provide a whole bunch of functionality, and come with Nix packages. Now, there's a lot of people who want those functions without having to import the entirety of Nix packages, which is quite a large repo, and also comes with package definitions and NixOS and a whole bunch of stuff, which is super great, don't get me wrong, but we want to break this out. And so what I've done is starting from scratch, just writing a library with all of the things you would expect. So all of our projects today are importable with flakes and non-flakes. So each project is contained in a subdirectory here, and you'll see that there is a flake.nix file. Let me shrink this source. There's a flake.nix file, which you can import in your flake if you're using flakes. If you're not using flakes, you can pull in this repository via fetch tarball and import this default.nix file directly. In fact, our flake actually just imports the same thing that this default Nix file does. So they work the exact same. Then inside of our source, we have our own library that does not include any package definitions. It doesn't know what packages are. It doesn't care what packages are. This is all purely Nix operations. And so we have the entry point here, this default Nix, where we glob together all of our different parts of our library and merge them. That's all this file does. It's 82 lines, but the code here might look a little awkward. Really, all it's doing is grabbing each one of these files, which looks like this. That is a function that takes the library itself and adds some stuff to it. And then we merge all those things that have been added. So that way you get one library with all of the helpers on it. So let's take a second and just kind of cruise through what's in here. And we're going to go kind of quick because if you're familiar with Nix packages lib, all of the stuff here will look familiar. For example, adders operations, any stuff happening on an attribute set is all things you're familiar with from Nix packages lib, right? So you can merge stuff, you can merge things recursively, you can grab stuff from a nested attribute set via the path, you can do all of the same operations you can from Nix packages lib, and that's because this isn't some totally new thing. This is built on top of the work that all of the amazing contributors to Nix packages and Home Manager, NixOS, etc. have done. And we've changed a few things. We've changed some of the names, and we've changed the organization. So now, unlike Nix packages, the library does not have any top-level exports. What does that mean? Well, you can't do something like lib.makeForce because makeForce isn't on lib, it's in a namespace. And we've done that to try and improve the intuition that you have when using this library. to make it easier to know, oh, I need this thing, it works on Booleans, therefore it's in lib.bools, for example. And the same thing goes for any module operations. If you're using stuff with modules, you want lib.modules. And all of that should hopefully be more intuitive, easier to reason about, and that way we don't have just a bunch of things sort of smattered on lib and then some things in namespaces. Instead, it's all ideally organized to make sense. Some of the names have also been changed to hopefully kind of map to your intuition a little bit better. Some of these names might be better, some might be worse for some people, but I have tried very hard to choose things that would be reasonable for someone to guess and expect that this kind of thing is here. For example, map recursive is hopefully a better name than perhaps what niche packages chooses for that name. And so there are going to be differences from niche packages lib, but not functional differences. And that's I think the important thing here is everything you can do with niche packages lib, you can do with this lib. So if today you actually wanted to use a niche library a la niche packages, but you didn't want the package definitions, you didn't want the NixOS stuff, all of those module declarations, you can actually import the labs lib today and start using it if you wanted to, if you just wanted pure niche operations. So a great lightweight alternative. We also have operations on strings and things. Let's go through these in order though. So we have bools, the same stuff you're used to, and this is one additional pattern that I have added, which I thought would be helpful ideally, is there are a lot of times where we want to do conversions of types or conversions into particular values, and I have used kind of inspired by Rust's from into system this sort of pattern where in these namespaces, so here we have bools, for example, so all the helpers to do with bools are here. And in this namespace, we have an into attribute set. And that attribute set allows you to turn bools into something else. So ideally, it makes sense where you can say lib.bools.into.string, pass it your Boolean, and it gives you back the string representation of that Boolean. And same with lib.bools.into.yes/no. You can pass it a Boolean, and it'll give you back yes or no, depending on what that Boolean value was. And this is hopefully intuitive for people. I'm still trying to figure out the best way to present this, but I liked the way that it's written a lot of the time. We also have the directed acyclic graph stuff from Home Manager. So huge shout out to the Home Manager contributors. Seriously, like I think this should be in Nix packages, and it's not currently, to the best of my knowledge. But we have it here. So you can create directed acyclic graphs so that you can represent some really useful dependency information just in Nix. And this lets us do some more advanced things in the module system, like what Home Manager's modules do. It's very cool. And so in this file, you have all the stuff for your DAGs. So you can create entries, you can create a single entry, you can validate them, you can do a whole bunch of those operations that you expect on a graph. We also have a helper for errors here. This will grow to include some common helpers from niche packages lib, things that you would expect, you know, add warnings instead of just traces, things like that. But we're keeping it as minimal as possible is the idea. And especially with this initial version, just getting enough to kind of move forward with the rest of the things that require this library, which I'll show you in just a moment. We also have some functional programming utilities, some just basic concepts that are helpful kind of everywhere. I've grouped them here in this FP file for functional programming. So we have, you know, your IDs, always return the same value, composing two functions, piping between functions. We don't do compose any or compose all for the same reason that niche packages lib doesn't suggest that you do that. It's a little more readable to just use pipe if you're combining more than one thing. And then flipping arguments for functions, which ideally you don't have to do, but you know, it happens. And then some helpers that you may not have realized are in Nix packages lib, but you should be using because they're super awesome is this with dynamic args thing. Has a different name in Nix packages lib, but here we're calling it with dynamic args because it lets you turn a function into a function that accepts arguments dynamically. What does that mean? Well, when you create a function in Nix, you can actually get the function arguments with a little helper, this built-ins.function args. And so if that function's argument is a destructured attribute set, such as if this were instead of lib was something like this, where we're pulling stuff out of, say I pull the FP stuff out of here. This would be a destructured attribute set. And so if that is the case, you actually get a list of those names that the function is pulling out of that attribute set. And so what you can do is dynamically pass the appropriate values instead of having to add the ... operator, which you might be familiar with. So instead of having to do this everywhere, you can instead just specify the thing you want and it just works, which is so nice. Awesome. So that's with dynamic args, and we'll see that used later to improve some use with the module system, actually. So generators. Generators, this concept totally from Nix packages lib. The idea being we want to often generate like INI files or JSON files or YAML files or TOML files and so on and so forth. And this concept is incredibly useful. So we have the same thing here, and it works the exact same way. The implementation is from Nix packages lib, again, standing on the backs of giants here. And this is currently just implementing a prettier, like a prettify generator, so that you can turn Nix values into a pretty representation. Things that you couldn't just cast into JSON, such as functions, are represented here. So if you have some attribute set with functions or other values that would not be able to be turned into JSON, you can use this generator and actually get a string representation of the value instead of just having an error blow up in your face when you try to cast it to JSON. Now importers. So importers, again, a concept from Nix packages lib, that's the idea being you do this a lot, where you read a file and then you say from JSON, from TOML. You're using the built-ins. Nix packages lib puts this directly on the lib itself and calls it import JSON, import TOML. I've abstracted this a little bit to be this importers namespace. We can add additional things in here that are useful. Right now it's just the same. Licenses, all the same licenses that were in Nix packages lib have imported over here to support all of that. It's the exact same information and the exact same structure, and it exports them in pretty much the exact same way, giving you access to all of the licenses. We also have operations on lists. Now, similar to that into that we saw before, was bools.intoString, we have a from here where you can say create a list from any value, which can be quite useful. If you already have a list, you don't need to make a new list. And if you already have a value, you want to pop it into a list, you can call list.from.any and use that way. It's nice and easy. So all of the usual helpers that you expect from lists are also here. I didn't mention, but some additional things like all of your sorting algorithms and stuff, searching for things and so on. The same operations that you expect from Nix packages are in here. And ideally, again, they have reasonable names that you can just find these without much issue. And the files are rather small, which is helpful. All right, there's a little math namespace, because I kind of didn't know exactly where to put these that made a whole bunch of sense. But this kind of works where you can add a couple common math helpers, such as min and max, and deal with things like that. Modules. So we do have the module system. So this is the entire module system from Nix packages. However, some things have been modified, some things have been changed. Not just names, not just organizations. Some functionality is a little bit different, which is important to note. Some of the big differences I'll point out when we're looking at some module definitions. But just know that things like submodules are a little different in how this works, and we don't support the shorthand syntax for modules directly. Only in submodules is that supported. And the idea there being that it's harder for people to confuse what is a module and what's going on there, which tends to be a common pattern when people are using NixOS, is they kind of don't know what a module is, even though they're writing a configuration.nix file. And ideally, this helps to make it more clear that you're writing a module, this is your addition to the module set. And similar, we can create modules from JSON, TOML, and so on. And all of this culminates in the modules.run, which is the equivalent to Nix package's eval modules. Here we call it run. So run a set of modules, give me the output, that kind of thing. And it works the exact same way with similar arguments. We don't call these special args, we just call them args because we've separated the concept of dynamic and static args as opposed to args and special args. The difference being there's some arguments that are from outside of the module system that you want to use in modules, but cannot be made configurable within modules, and for reasons typically of recursion. And so we use that concept here. We say we have static args, which are the args that you pass into this run function. We also have dynamic args that are supplied by modules to the module system, and so you can customize these and add these at runtime, which can be quite useful. Numbers, similar deal as before. You have a handful of helpers for converting numbers into a particular output, whether you want to turn it into a string or a hexadecimal representation or target a particular base. Some common helpers there. This is also a part of the module system, are options, right? You create options for modules, and so all of those things are in here. These are separate from modules because realistically, options are their own kind of concept. They do a lot of their own things and they interpret themselves. And we have a whole bunch of code that actually looks quite similar and runs the module system itself. So we have run over here for options, which will let you evaluate options, right? So similar to what Nix packages does, but we've changed some of the names and a little bit of how a couple of things work. Packages, I mentioned that packages are not a concept in here. This packages namespace is intended to be extended by whatever uses this library, because right here, as you can see on the screen, the only thing it actually does is operate on a derivation and hardly even that. You can check if something is a derivation, you can sanitize a name to be used for a derivation, and you can get the output of a derivation. These are just core Nix concepts. There's no concept of a package, there's no concept of meta information, none of that stuff. Paths. So paths, again, core Nix concept, and much like strings, you see a lot of the same operations where you can turn it into, for example, a derivation or something that looks like a derivation perhaps, and use it in places where you would normally use a derivation to get the same functionality. You can also validate certain things about paths, and this validate pattern is something that we have in multiple of these namespaces, where you can validate particular properties of a type, which can be quite useful. Here, validating, for example, that a path is in the Nix store, and a handful of other little helpers to construct, say, paths that search for the bin output of a derivation, the lib output, and so on and so forth. All right, so fixed points. I've put this in points over here, at points.nix, or points/default.nix, I should say, and it functions the exact same way as Nix packages. This is a bit of a weird concept if you haven't delved into it, but because Nix is lazily evaluated and functional, we can do some clever things, such as passing a function and then sending that function its own result until it settles and returning the results. It's kind of clever. So that's what a fixed point is. It takes a second to think about. But this is just a little helper to do that because it can be quite useful to effectively extend this single output with multiple iterations. We also have this with extend helper. This is what Nix packages called make extensible, but it also required passing an attribute name so you could customize it. We said here that it should just be extend all the time so you know where it is. So we called it extend and don't give you an option to customize it. If you really want to customize it, I guess go make your own. It's only a couple lines. But realistically, this will help. So if you see extend, you know what it is. It's from this with extend thing, and it means that you can call that extend function and add on some things to whatever value you're operating on. Okay, strings. We have some ASCII and alphabet operations, which is what those little helpers, what those little files are, just containing the alphabet and strings and stuff, because Nix really wasn't designed to work on strings, not really to operate on them in the way that does. And so we have to be a little bit clever. Converting things to, say, ASCII, we just look it up in a table. And same with like all the other operations that dig into stuff. And so you have a handful of helpers, same stuff as what's in Nix packages lib. Again, ideally organized to where you can find these things without already knowing where they are, and you can go kind of exploring in the REPL a little bit easier. So we have types, so the type system for the modules system, of course, and types can be used on their own, sure. We have them separated out here because there are a whole bunch of implementation details. So types have a lot going on in them. We won't dig into them here. I'm considering doing a whole thing on the module system later because it's very cool. But suffice to say that we have the same type system which allows you to create these objects which include information about checking against a particular type, asserting it's correct, merging multiple values of that type if that's a thing that you want to do, and submodules and all that goodness. So all the types that you would expect from Nix package lib are here, such as any, which Nix packages calls anything. There's an unspecified type, which I'm not sure if it's in Nix packages lib. I feel like it is. But we have bool, int, there's ints where you have like ints.positive, ints.unsigned, ints.u8, and so on. You get the idea. We're namespacing some of these things so that it's clear. Instead of just calling it uint8 and having everything slapped onto types. We have float, we have numbers, numbers.positive, positive or 0, ports, version, string, strings dot, a whole bunch of stuff with this, lots and lots of options, but all the same concepts from Nix packages are in here, which again is a running theme. I very much want to stress that we're standing on the backs of giants here, and a huge thank you to all of the contributors of Nix packages making it possible to, not have to do all of this from scratch, which is very nice. Now, all of this was actually written by hand. None of this was copy-pasted, except for, I think, maybe one or two cases, say licenses, I believe, started with copy. You see there's a couple of comments here and there. But the majority of this was written by hand. Even so, this is like why the license is the license from Nix packages. That's why it includes the home manager license as well. The whole point here is this is built on top of those projects. All right. We also have some version checking stuff, so you can do things like check if a version is greater than or equal to. And again, I'm kind of spinning around, and we're just going through here to show you that all the same stuff from Nix packages is available in here. And so you can make use of it today if you really wanted to. Awesome. So that's lib. And if you wanted to use lib, you could import it using that default.nix, or you could pull it into your flake. So here we have another project called Foundation that actually imports lib to use it, and it uses the module system. So if you wanted to do the same thing, you could point to the Aux Git Repository. So you could say, axolotl.org/axolotl/labs dir lib to point to just that. Or if you're not using Flakes, you can import that tarball and pull in just that default.nix from the lib directory. So what is Foundation? Well, there is some awesome work that Emily Trout has done in Nix packages to create a binary bootstrap based on the the Geeks binary bootstrap, which is super duper cool. So it's all building off of, and if I remember correctly, it's a 375 byte assembler. So it's a 375 byte binary file that is an assembler, and that's the only precompiled thing in the entire chain. It's super cool and has been in Nix packages for a little bit, and some stuff I believe is still in a PR if it hasn't been merged by the time you're seeing this. And the unfortunate thing is that it's not actually used just yet to create the whole package set. Nix packages is still bundling a larger set of bootstrap tools, these precompiled binaries that include things like bash and a C compiler and stuff in order to actually build the package set. And there are benefits to that, sure, but there are also problems from that. Now, trusting several hundred megabytes of code to not be malicious, which is much more difficult than a 375 byte file that you can inspect because it's actually just machine code. And it's quite well documented as well. So heavily recommend checking that out. Huge shout outs to Emily Trout, who helped me immensely as I was going through re-implementing this work using the module system. She is so gosh darn smart and very helpful. So thank you so much. Now, this package set, as I mentioned, is built using the module system, which is not something that Nix packages does. And I wanted to do this for a couple of reasons. I felt that the structure imposed by the module system that you get from things like NixOS helps a lot of people get into making changes that they might not otherwise have thought they could make, because you have this concept of building packages. And in Nix packages, you have to call functions and use some helpers and know the particular things to set, and you don't quite get type checked, so it can be a little difficult. And you sort of have to know already exactly what you're doing, and if you don't, you run into issues. The module system lets you at the very least experiment and tells you, hey, this thing's wrong, it's the wrong type, or this thing has an assertion, you need to go set this if you want to do what you're doing, which can be quite useful. It also helps us glob all these things together more cohesively. We can refer to packages more easily. We don't have to worry about a lot of recursion shenanigans because the module system just kind of takes care of it for us. So we have this entry point for our flake, right? And the default Nix does the same thing here. Wrong default Nix. There we go. The default Nix does the same exact thing here, importing the source and giving you all the packages that are defined. Because this project here, Foundation, declares all of the infrastructure for itself, all of the modules, all of the types, all of everything to do with creating packages in the module system. And that starts with exports here. We have this exports option that is set by other parts of Foundation to export packages. And so we can export packages and additional extra things for help debugging, typically, is what's used there. And in here, the big deal with Foundation is that it's all building from scratch. So we have a couple different concepts of builders. So these builders follow a common pattern where they have a build function. And so you can see we have a raw builder, which builds using built-ins.derivation. And that's actually all it does. It calls built-ins.derivation, and you can pass it a builder and a name, and there you go. It runs the derivation. Now, eventually, we want to go from this to a more fully formed builder, much more similar to stdinv in niche packages lib, right? That make derivation function that gives you a standard environment and can build projects without much configuration. But we're a ways off from there, because in order to start, we have to go through stage 0. This is broken into 3 stages. Stage 0 here is focusing on that initial bootstrap, right? Where we take a 375 byte assembler file, we build itself using itself. So we assemble its own source code. And that's it. That's all this does. So we get an assembler, and we use that to build a slightly more advanced assembler. And we use that to build a slightly more advanced assembler, and so on and so forth, building these packages to then be able to do things like combine files together so that we can then do some cool things like build an actual Linux binary via the hex output of one thing and an elf header that has been like pre-written. So we combine those, build an actual binary, and continue working through this. And again, all of this is thanks to the amazing work of Emily Trow and all the Geeks people who have done some fantastic work. And we continue here building these things up to get slightly more advanced and slightly more advanced until eventually we're able to compile C sources. And that's what you're seeing here. Eventually we're able to start compiling very simple basic C sources and producing our own binaries, generating that Linux executable format header, and moving from pre-compiled binary to now we've compiled an assembler to now we have an actual like tool chain, which is so cool. And we just keep going and keep going, and then eventually we end up with this really useful tool called Kime. I hope I'm pronouncing that correctly. Kime is a shell for systems without a shell. Think Bash's little brother, I guess. It's super duper simple. It only supports very basic syntax, but that's all we need at this level. And so we can do some really cool things like use it to build itself. So here's a Kime build script. There we go. It just looks like a shell script because it is. It's a very simple one, mind you, but it is. And so now we can actually start writing install scripts. Cool. So that's stage 1, is we end up with just enough to run some basic shell scripts and compile some basic C stuff. Stage 1 here, sorry, that was stage 0. Stage 1 here is where we start getting into all of the tools that you're probably familiar with or have at least heard of. So we start moving to TinyCC, building that up. Initially, a very simple version built with what we had originally, and get the job done, get a slightly more advanced C compiler, then eventually building one with messcc utils, fantastic, and getting a slightly more advanced C compiler, and then building it with muscle and getting a more advanced C compiler, again, now built with a modern library. So as we step forward, we're able to compile more and more and more and build more of these programs. So we can get up to bin utils, and then we can use that and Bison and build GCC, right? Build an old version of GCC, of course, because nowadays it's written in C++. So build an old version of it, build the C++ stuff, then build a newer version, and then eventually build an even newer version. And same with all of the other stuff in here. It's the same concept of we're building, starting from scratch, what do we need in order to build the next thing? And we build all that stuff and then move on to the next thing. And so that's stage 1, is we get to having functional tools such as Bash, GCC, we have like Linux headers and all of the goodies that you would expect in order to be able to create still basic, but common programs. Stage 2 adds a couple more things, such as glibc. We also have busybox, bzip2, patch elf is a big deal for Nix. And so a couple of these additions, as well as you'll see some duplicates from stage 1. These are all statically compiled versions. And so we have additionally just static versions of some of these programs, ideally making them easier to kind of port. All right, so that is stage 0 through stage 2. We end up with a fully functioning package set now that we can actually use to, well, ideally create a bigger package set. So this only includes a handful of things, is the downside here. But that's not a problem, because the point was binary bootstrap. Get us to GCC, get us to good enough. And that's what this does, all again using the module system. So that gets exported. We have a set of packages there. We have our lib. Now what is this Tidepool thing? Tidepool is super cool. And I'm not just saying that, I am proud of it, but it is genuinely very cool, I think. Using the module system is a big deal for the reasons that I've mentioned before, but using the module system for everything is really nice, as it turns out. Being able to kind of not deal with flakes, kind of not deal with all of the cruft of individual systems, and just instead rely on modules makes things a lot nicer to work with. And you also get a lot of really fascinating benefits because of it. So this is using the module system to do, again, everything. And we're creating a larger package set. And this time, that means we need additional helpers. So you'll see there's this lib here, because that actually adds a lib option that extends the default Aux Labs lib. And so we add on some helpers to that. For example, getting dependencies of packages, getting additional information from packages, and dealing with hooks, and building packages, right? So that's a thing we need to do, and so on. There's a bunch of cool things that I'm about to show you in just a second, but bear with me as I give you kind of the lay of the land. So all of these helpers here are added on to config.lib, which can then be used anywhere in, well, the module system, which is super cool. You can pull in lib here. Typically what ends up happening is you don't end up using the lib that's passed in by default, and instead just pull it in from here, from config. Nice. So packages. How do we declare packages in this system? Well, it's modules. So you might think, well, maybe you declare like the derivation for the package at an attribute, which is not what I want. I want to be able to fully configure these modules. I want to be able to fully configure these packages. And I want also to support multiple versions of packages, as I felt that was a shortcoming of Nix packages, not having a great way to do that. So packages follow this format. We have this packages namespace. You get your own namespace here. So you get one level. And then in there, you get the name of a package. That package has a versions option. In there, you can specify definitions for individual versions of your package, including aliases like latest and stable. So each one of those versions is a module on its own. And I don't mean that it's just an attribute set. It's not just some object. It is a module that is then fully evaluated later. So you can use all of the same things that you expect from the module system to make this fully dynamic. You can add additional options to your package, and you can even do so from elsewhere in the module system. It doesn't have to be done in here. Elsewhere, I could say packages.aux.b.versions.latest and set options blah, 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 and it will work. So all of that same stuff. And then because we're defining the concept of a package in Tidepool here, we have this type declared. So this type is maybe one that you haven't seen before. It's a coerced type. So if you haven't been super deep in the Nix packages lib and the module system, you might not have actually known that there's this types.coerce thing, which is actually incredibly useful. It lets you specify a type that starts as one thing. Users can pass one type. Then there is a transformation that's applied to that value to yield a final type. And users can set either the first initial type or the final type, but if they give you the first one, it applies that transformation automatically and yields the final one. So why is that important here? Well, the module system lets you do some really cool things, but one thing it doesn't let you do is this, or the simpler version of that, this, where you set the output of, or rather, if you have a submodule and you set its value to the value of some other submodule from your config, you'll end up with defaults being applied, which in a lot of cases may be what you want, but in a lot of cases may not be what you want. And here, that's not the case. What I actually want to do here is specify my package named B as a dependency here. So I want to set B equals packages.aux.b. And I want the full package definition brought over so that I can customize it. I don't want it to just be a static value. I want the whole module here so that I can say deps.build.host.b and say, maybe .version equals a custom version or .this equals something else. I want to be able to customize it on an individual level. So each one of these needs to be the entire definition. Now, that doesn't work out of the box. But if you, instead of using just a submodule type, use a coerced type, you can grab whatever values come in and choose what goes out. And so I actually capture all of the modules that are specified, that are defined for submodules when you set these things, and pass them through. And the final value is actually a brand new eval of those modules. So you get the full force of the module system. None of this is ever cached. None of this is ever static. We get a real eval of the modules. And some of you that might not get what I'm saying might not understand, but that's a huge, huge deal here because it gives us so much potential for dynamic things. This is, for all intents and purposes, portable packages. You can bring a package anywhere in this module system and the entire package definition comes along and will be reevaluated when it's used, which is so useful. And not just for packages. We haven't gotten there yet, and not because I haven't showed it, but because we actually haven't implemented this yet, because we're still working on some foundational things. But services would benefit dramatically from this. Imagine for a moment not having a difference between a systemd service, a home manager systemd service, a run init service, or any other init system, whatever you want to deal with. You can move these services around and the entire definition comes with. We no longer have the problem of you have to implement systemd services for the system, you have to do it for the user, you have to do it for home manager. All of those can use the same exact definitions and can be customized uniquely. So we get the best of all of that, which is huge. And that's a thing that's got me really, really excited and is why I would love some help getting farther in this project. All right, so that's we have packages here and they are these modules. Now this type that we're specifying here, we have a lot of the common things that you expect from Nix packages. So we have metadata, for example, that you can specify, defaulting to just some kind of blank values. We also have some extras. This is called pass-through in Nix packages. I felt extras was a better name for this, as additional things that you're adding onto the package that are not the package itself. We also have some, platform information, what platform we're building, host, target, and stuff like that. We also get the name, which is automatically calculated from the pname inversion if you choose to use that. Still undecided if the pname is the best wording here, but we do what we can. The builder, which is similar to that concept in Foundation that we saw for builders, where a builder has a build function. And the idea here being you can swap in builders. So if you just needed some basic thing that can build a simple package using built-ins.derivation, you can do that. Or if you have some more advanced thing that is, say, building a Rust package, that it can target just for that and know how to build Rust packages really well. And it's as easy to set as saying builder equals builders dot whatever one you want to use. We can also customize the environment, which is a little bit more clear here, instead of the Nix packages way of just setting stuff directly on the attribute set you pass to make derivation that kind of flows through to built-ins.derivation. What you actually end up here with is env, and you're setting specific things that you want to decide. Let's see if I do that anywhere so I can give you an example. I think perhaps in here we might find one. Yes, so env, I'm setting path, for example. So a little more clear, easier to reason about ideally. The package is available. So this is the built package, the one that the builder creates. And you can actually see here, it's just created by calling the builder on the config. Cool, right? It's pretty simple. We also have phases. Now, this is, I believe, a shortcoming of Nix packages build system, that we don't have super configurable phases. What I would really love would be a graph of these phases that you can add nodes to and dynamically construct this build plan. And so that's what we actually have here, and that's what we use our distributed acyclic graph for, the thing that we pulled in from Home Manager. And so phases here actually can be defined as whatever you want, and the builder might have some default ones such as unpack, patch, configure, build, install, but those are no different than putting any other text in here. And importantly, what you end up being able to do is choose where some of these things go. So for example, in here, I can say like lib.dag.entry.before and make sure that this one runs before unpack, which is really useful. That's not a thing that we really can do easily in the Nix packages build system. You have to deal with these hooks and remembering to, run a hook before each of these. No more of that. Instead, it's all managed in this graph, and everything is combined together in the way that this graph determines. And not only that, while I'm here, the next thing to talk about is context and hooks. So this is where the extensibility really comes in. You can specify hooks, and these are a little bit different than what we have in Nix packages, because these hooks are just build phases. So it's additional build phases that you're adding, but only when this package is a dependency of another. So for example, the compiler package, so GCC, maybe you use that as a dependency for your package so that you can compile a C program. Well, this GCC package can have these hooks specified to automatically set up all of the environment stuff necessary in order to compile. It can automatically hook up all of your library paths, all of that, and make sure that things can build correctly. And this context concept, I'm not sure if I'm using it anywhere, but let me see here. This concept, context concept is an ability to share values with other hooks. So I can say context here, and add some values that will be applied to hooks. So if I set, a equals true, this hooks value here is a function which takes the combined context of all those packages and can then use them. So what can be really useful is setting information for those hooks to use. So for example, if you wanted to include something, and there's some important C thing or library or something like that, you can do that. Or if you wanted to inform a hook to operate a certain way, you can do that here, which can be very useful. And because this is all modules, all of that can be configured after the fact dynamically. So you're not actually stuck like you often are with package definitions where you need some weird override adders combination. Cool. We also have propagating packages, and this one's pretty interesting. So let me see if I am actually using it anywhere. And I don't think, oh yeah, I am in B. Okay. So when you set propagate on a package, its hooks will be used even if it's not a direct dependency. So this is very, very useful for things like Python. And this is the propagated packages setup that Nix packages uses, but they have multiple additional inputs for just propagated packages. You have build inputs, you have propagated build inputs, and so on. Here, we can actually just set it on the package itself, and we can even override stuff on the package or extend the package to customize a new version of it and set propagate so that any things that are defined as hooks here, oh, there we go. See, I'm declaring some context. So anything that's hooks here will be used anywhere that pulls in anything that uses C. So not just C directly, but here in this example, we have package A. Package A depends on package B. Package B depends on package C. And for package B, we've set its C dependency to propagate. So that means A over here, which uses B, but does not directly depend on C, will still have the hooks from C applied. So things like Python, you can package programs that use Python and still pull the Python runtime along nice and easy, even if you pull those packages into something else, right? So even if Python isn't directly dependent on, it will still be pulled in. So you still get those hooks, you still get the package, it's still available. And there you go. That is our package type, I believe. Oh, no, we didn't talk about dependencies, but it is very, very similar to what we have in Nix packages. Nix packages, you have this concept of like build, host, target, and that comes from C compilers pretty much, having build, host, target, or mostly GCC. And so there are these different ways that you can target things. You can target things for the build environment. You can target things for the host environment, for the target environment. And maybe a better way of me saying this is where you want this dependency to be used. And you can have it on the machine that's building the package. You can have it on the machine that is running the build package. Or you can have it used for code that is generated by the program that is later run. And so each of those is build, host, and target respectively. And there are different combinations here of where you can say, have a thing that is intended only for the build environment, or it's intended for the build environment, but will produce something for target, or builds package that is then intended to be run on the host and then targets the target, a bunch of stuff like that. There's a lot of combinations here. But the best part about all of this is that it's super simple to use, because earlier we did all the work for that package definition to be portable. So you can just drop a package on here and say, yeah, I want package B to be for my build environment, and I want it to be built for host, right? It's the build is set to build, host is set to host, and target is set to whatever it's set to. And so you can do all the same things that you would do in Nix packages, but here it can end up being a little bit easier sometimes, which is quite nice. And of course, all of these can be configured after the fact. One thing that I didn't really cover was extend. So extend lets us do the same thing that almost like a combination of Nix packages override and override adders. If you've used either of those or both, you know that they sometimes do what you want, and sometimes you need the other one, and sometimes you need a combination of both. So extend lets us modify a package, okay? And not modify it in place, as in, you know, mutate the package, but rather it lets us take the modules, those module definitions for that package, and add another one to it, and then give us the result of evaluating all of those together. So I can make changes to a package by calling extend and passing it a module. You can even pass in a list of modules, if I remember correctly. And so C here does not have propagate by default. You'll see there is no propagate in here. But here I am extending C to add this propagate value so that it will now propagate. I can change anything in here that I want. I can add additional hooks. I can remove hooks by, you know, overriding them. I can add additional phases in here. I can change the name, the platform, whatever information I want to, I can modify in here. And so you get the benefits of all of the configuration from this, because like override, we have some things that the creator of this module can make easily customizable with options, right? Similar to how override lets you override the arguments of a package definition in Nix packages. We can use extend to set some config for options that exist on this package, but we can also use it to modify any existing thing on that package or anything on the package type definition, which is much more like override adders. The difference being that in this system, because everything refers to this config, we no longer have the issue of setting something using override adders doesn't actually recurse around and update all the other places that would use that. Here it does, because we're referring to config, because we're referring to this module's output. Very cool. So that in a nutshell is Tidepool. And where have we gotten with it? Well, we've gotten all the way up to GCC, pretty much. Sort of where Foundation ended, right? Where we had that stage 2 and we built GCC. So why hasn't this gone any farther? Well, one reason is that I'm not a C programmer, unfortunately. As much as I maybe wish I was in order to get through this, part of the problem is I haven't worked with these tool chains, and I really don't know the ins and outs of GCC, the C language, the build system, or any of the related tools. And that's made a lot of this tough. And the thing that we're stuck on right now, or I'm stuck on right now, is trying to get a cross-compiler built. Right now, all of these packages are built for i686 Linux, okay? That means we're not building x86-64 packages, we're not building AART64 packages, it's one platform. And the only thing we can build for is that one platform. I really want to be able to cross-compile over to x86-64 and then start producing more things for every platform, right? So that way we can have cross-compilation from the get-go. I think that's a really important step, and so that's why I've been hammering away at this, trying to no avail, unfortunately. So if anybody out there is familiar with cross-compilation, is familiar with building GCC, is familiar with the C build system, toolchain, any of that stuff, and you're interested in some of this, please feel free to get in touch. Hop on over to the Aux Git Repository for Labs. I will leave that in the description. Please feel free to file an issue and say, hey, I think I could take care of this, or submit a pull request, or get involved in any way if you want to start jumping in. You can always head over to auxolotl.org and check out some of the links there for the community. We have the forum, the matrix service, and we also have our Forgeo instance. You can jump into any of those, say hi anytime, and links for those, of course, will be in the description. And hopefully, with your help, we can actually get this project really moving. Cross-compilation would be huge. Being able to target different architectures without any additional work would be awesome, and we can make that happen with this module system. And then finally, building up towards a full package set. A full package set that we can replace Nix packages with, which I think would be awesome. Thank you all so much. I really appreciate those who stuck around, who found this interesting. Again, if you want to get involved, please feel free. Drop me a line anytime. I'm happy to chat. And until next time, I'll see you later.